Lecture 28, Causal Profiling. At this point, we've got some experience in identifying some areas of the program that we think are slow, or at least limiting the maximum performance of our program. If we are presented with more than one thing, the question arises, how do we know which of those things, if we optimized it, would yield the most benefit? Is it possible that optimizing something would actually have no effect or a negative effect? Well, the scientific approach is, we do an experiment, we see the impact, and then we reevaluate. So we make a change to the code, and then we rerun our analysis, whether that was a benchmarking suite or whether we just observe the system as it is executing, and then we make a decision about whether that helped, and if it did, by how much. Reevaluate in this situation. What we're going to talk about today with causal profiling and not casual profiling is this idea of running experiments without changing any code. And that's potentially a significant savings in terms of time and effort, right? If we can work out in advance, this adds 10% benefit, and that adds 12% benefit, and this adds 27% benefit, we know which one of those is the best because it adds the highest amount of benefit. And we could actually do that without changing the code, deploying it, seeing what happens, all of that extra stuff. And that's the real magic of this causal profiling, is we do the what-if scenario without needing to actually change any code. And the example that we're going to talk about today is a profiler called Cause, spelled C-O-Z, but pronounced like cause. And it does a what-if analysis that helps us to get an estimation of what would happen if we sped up a particular part of the code. Okay, that doesn't sound like anything all that special, because you could say, listen, if I just look at the time and I see that a certain amount of time is going to the work function, we could easily do a calculation that says, well, if the total time of the program would be reduced by some amount by multiplying the fraction of time spent in work versus the fraction of improvement, and then we would get an answer. And that's a very crude, although not totally unrealistic model in terms of figuring out what would be the impact of optimizing this particular piece of code. The problem is it's not actually going to reflect reality, right? It's not that simple. What we really need is a simulation. Right? Speeding up a particular function by a certain amount potentially produces some good benefits. Ideally, it is a lot of benefit, but it's not a guarantee, because speeding up that particular function might not make that big of a difference. It might actually increase execution time by increasing, say, lock contention or some other mechanism. It adds things to the critical path. It just doesn't work out quite the way that we're thinking, so it's not as simple as we'll just guess what happens if we speed this up by a certain amount. And here's the observation that the authors of the cause profiler show, and they show it in their paper where they explain the nature of this tool. And it's the idea that speeding up one area of code is fundamentally the same as slowing down every other part of the code. So it's all relative, right? And this is what it calls a virtual speed up, in that sentence referring to the paper that contains the explanation about the causal profiler. How is other code slowed down? It's very simple. It's very straightforward. There are just pauses added to the code to make it take longer to execute, such that other things appear to be faster. That certainly makes other threads run slower. There's no getting around that. But one of the things that you might be wondering about, and I was also fairly skeptical until I sort of looked into it myself, is this really equivalent to speeding up the target? Is slowing down other threads the same thing as speeding up the one that we want to speed up? Well, here's an explanation that is provided by, again, the paper authors in visual form. With the original runtime of the program is A, So we have a function in thread 1, it calls f, then g, then f, and then thread 2 calls g, then f, then g, and we have to do these things in parallel, so the total time is the maximum of whichever of those it is. And then if our goal was to get an actual speed up by reducing the amount of time that was spent doing the function f, then we would see again the same behavior, and there would be an actual amount of speed up. And the question then is, well, if we slow everything down, so we pause other threads while we're executing this function so that we can simulate the speed up, then does that work? Yeah. And the paper goes into some more details about the specifics of how it works and how to interpret all of these things, but hopefully you will take this as being somewhat convincing based on what we see here, right? And when we optimize f, when thread 1 is running f, then we pause thread 2 to produce the value of how long it takes for thread 2 to execute function g. And when thread 2 is running f, we pause, and that happens to pause while we're running function f, but that's okay. And so on for the third one, meaning we get a total time, and we can see what the virtual speedup would be, and we can see that the virtual speedup is the same. Okay, so given that you believe me, I hope, how it works, here's some interesting kind of observations about how the tool provides some graphs about potential speedup for your program. So here we get another layer of what if. It's not just what happens if you speed up a particular part of your program by X amount, but it actually shows a graph of more speed up results in the following behavior for the program. And it's done in this case using a sample program that has a bunch of different functionality, searching and sending and organizing. It doesn't matter what they are. Each different color corresponds to a different part of the program doing a different functionality. And for some of them, we'll see no impact at all. Saving, speeding it up doesn't do anything. That might actually make sense just from an intuitive level. If saving is limited by the disk speed, then actually nothing we do in terms of making the program run faster would make any difference. But this is a sample scenario because it's a pretend application that shows all possible outcomes. And one of them is continuous linear speed up. That's the red one. The yellow one is showing we have some speed up, but it's capped at some point where we've reached a maximum. We have orange, which doesn't show very much speed up at all, and we sort of reached the maximum there quickly. Green has no impact, and blue has some situation where actually it gets worse if we speed that up. It's relatively easy to imagine scenarios that correspond to each of these things. It's just really a question of your imagination, right? If we're computing the n-body problem, well, any speed up is going to result in a massive improvement. So we should expect to see behavior that's kind of like the red line, which is if we could do it any percent faster, that's always good. It always improves the outcome. So there's kind of no limit to that. And then we can imagine that optimizing something has no impact because it's not on the critical path. Green in this case, like I said, saving, if that's limited by disk speed, then it doesn't really matter how much we do CPU profiling and improvements on its execution time in terms of code because we're limited by the disk no matter what we do. And then there are things where we can speed it up a little bit, but it very quickly reaches its maximum because it wasn't particularly critical or it wasn't a big part of the program. And then we can find some things that actually make it worse temporarily. And making it worse tends to happen based on something like increasing lock contention, adding things to the critical path, anything that would slow your program down is possible, right? Lock contention is just a good example, but it could easily be we spend more time waiting for the database, or we have to wait longer for disks because disk operations are now taking place concurrently. Whatever it is entirely possible that speeding up a particular thing actually makes it worse. Now, just because the profiler shows you that hypothetically you could speed up a program, if I go back to like the red line here, potentially, yeah, it'd be amazing if we could speed it up this way. But that doesn't mean it's actually going to happen, right? We can see there'd be a lot of benefit from optimizing the red code in the sample application, but there's no guarantee that it's actually doable to speed it up. Right? We still have to modify the code or change the algorithm or do something to make that happen. I think it's fair to say it's not possible to speed it up to an arbitrary degree, right? There are some things we cannot avoid. There's some limit to how much speed up we can realistically achieve. So we're going to have to assess what we can do and how difficult it would be. And then after we have made a certain change to the program, we said, okay, there's the most benefit comes from speeding up the red parts by X amount. Then based on that, we can rerun a new set of experiments with our new baseline and see what we can accomplish in that regard. So the source paper that covers this particular topic has a little table here that summarizes some of the optimizations that they've applied to a few different programs. And it seems to support the idea that, well, actually the tool can be used pretty effectively to get a meaningful speed up with relatively few lines of code changed. Again, if you want to read through the paper, you can get kind of a better look at some of the specifics about what is beneficial in these changes, and some of them are replacing one algorithm with another, some of them are improving caching, something like that. But these are actual programs. SQLite is something that I've written a little toy application that uses it, so it's not a cooked example where of course we can get speed up by just not doing dumb things repeatedly. So there is something to it. There is something there. There are some limitations, of course, right? This kind of thing works realistically only on one machine where we have access to all the threads. If we don't have access to all the threads that are involved in the execution, we can't pause them, so we don't get the behavior that we're looking for. We're not able to pause things that are not under our control. And that extends also to things over the network. If we are communicating with a remote server or something to that effect, again, it's very hard to get the remote server to pause at our command for the time that we need to make that happen. The network also adds a little bit of complexity based around the idea that communication is not instantaneous. So there is also a possibility that even if we could command the other side to pause execution or something like that, that the amount of time it would pause would vary just based on sort of network latency, and that would mess up our measurements a little bit. It is fairly challenging, right? We could maybe try to simulate some sort of network thing by like delaying incoming responses based on the speed up that we are expecting to get. Just like don't handle the response until we're ready. But the simulation gets harder and harder to manage the more of that you want to do. And in network communication, we do have to worry about things like timeouts where we haven't responded fast enough, so the other side has closed the connection. That sort of thing can just add that little bit of extra chaos that you really do not need in terms of actually executing and making sure it does what you think it does. One other thing, of course, that if we want to estimate the overhead for this particular workload, the authors estimate something like 17.6% overhead for this tool, which is broken down into 2.6% for startup debug information collection, 4.8% for sampling, and 10.2% is the delay caused by slowing down other threads such that we generate a virtual speed up. That's a manageable amount of slowdown. It's not the kind of thing you would do on a time-critical system or where you have very hard deadlines that you need to meet, but it is fairly reasonable for debugging. I would say it's actually pretty good in terms of if you just wanted to do some program analysis where you said, I'd like to figure out how to speed this up, then you're working off your machine or a special deployment that allows you to tinker with it sort of as much as you want. And for that application, this is actually quite good. So yeah, I think we could be fairly happy with that. If you're interested in seeing some more of the details of the tool, then there is an author presentation here at ACM Symposium, and the YouTube video here is linked. It is about half an hour long and is fairly interesting. Is something that you might learn something from. There's more details about it presented there, as well as some audience Q&A that may cover some of the questions that you have. But hopefully this is a good introduction to the topic. And then there's the next generation. SCAUS, SCAUS, I don't entirely know. I guess we'll see. But a few years after the original paper that we talked about and the author presentation that you may have looked at were published, some other researchers decided they were going to build on this idea, and they said, what if we could address some of the limitations of the previous system? And we touched on at least one of them, which was the idea of multi-process kind of application. And yeah, that makes sense. But also they wanted to address the idea of what happens when the operating system is running. Right? Looking into the kernel is not always permitted for a given profiling tool. It really depends on your permissions. And it is rather obvious to imagine that if you cannot look, then you cannot touch, i.e. you can't pause execution while you're in the kernel to give a virtual speed up for other parts of the program, making for, let's call it a limitation to the original idea. If indeed the kernel is a bottleneck, it may or may not be possible to do very much about it. Avoiding system calls is one of those do less work strategies that you probably already considered, but oftentimes doing the system call is because we must, right? We would love to make this this happen, but it requires some I/O or protected memory something, so we kind of just have to live within the limitations of the operating system. In an open source operating system, or at least a situation where we can install our own kernel module, we might have the ability to do something about it if Cause gave us some recommendations. So the approach in this new paper, it's linked in the notes, is to move from a thread-based system to a core-based system. So where previously, to simulate the speed up of a particular section of code, the tool would pause all of the other threads. Now it pauses the execution on all of the other cores. Okay, there's a little bit of complexity in that to try to ensure that costs are assigned to the right places. There's details about when one core wakes up another one, or there's idle cores. How is delay charged to the correct core? That's fine. I invite you to read the paper if you really want to get into the details on that. For our purposes, that's not actually all that interesting. We can just kind of proceed with an understanding that there is a solution to that problem. But yeah, what does the implementation look like? I mean, this diagram gives you kind of a similar idea to what we discussed previously, right? The original program, there's some threads, they execute on some different cores, and we can do some core level virtual speed up by inserting pauses, i.e. putting the other cores to do nothing temporarily to simulate what would happen if, say in this case, thread T5 happened to run faster. There's delay assigned to core 1 labeled D1 and delay assigned to core 2 labeled D2, right? Now there's some amount of complexity that this last part of the diagram labeled C shows, which is the idea that like when thread 1 finishes here, it's going to wake up thread 4. And there's an intended delay, but there's also a little extra delay caused by pausing thread T1 running on core 1 to try to make sure that everything lines up as it's supposed to. The implementation here involves a profiler thread for each core to manage its behavior. The thread is pinned on that core. You might have heard about like soft and hard affinity more than once, and its purpose is primarily to call the end delay interface with preemption temporarily disabled to stop execution briefly on that specific core for a given period of time. This extension does allow this scause profiler to do more, but does require running within the kernel, which implies certain limitations about how you can apply it. That's kind of an interesting trade-off, right? Because we don't always control the system that we are running on, which causes the occasional headache.